In this video we are going to discuss another variant of Turing machine, and that variant is multi-tape Turing machine. So its essence is present in the name itself, a Turing machine which will have multiple tapes, right? So multi-tape indicates the Turing machine is having multiple tapes. So usually we know that whenever we execute a Turing machine, we have a tape associated with that Turing machine, right? And this tape is one in number, and it has one end fixed and it is infinite on the other end. And this tape is organized in the form of blocks, where in each blocks you can have tape symbol, and apart from tape symbol you may have blank symbols also, right? And you have a tape head which points to the uh, current location of your tape head. Now if you have a Turing machine which multiple such tapes, right? So if I have tape 1, suppose, then this is my tape 2. Okay, it has its own set of symbols, it has its own tape head. Then we have, say, third tape. Again there are blocks, it also has its own tape head. Likewise I have n number of such tapes. Likewise I have such n number of tapes. So this is my tape 1, this is tape 2, tape 3. Likewise we have total n number of tapes. So each of these tapes will have their own set of tape symbols. So this will have its own toe, and there will be blank symbols apart from that. Each of these tapes will have its own tape head, which can take its own independent moves in the form of left, right, and remaining stationary. And your Turing machine diagram will also have states, right? So we'll also have state transition diagram, right? So this, for a particular transition that will take place in this multi-tape Turing machine, whenever you do a transition, suppose you are in a state, say Q0, okay? So from Q0, when you are performing transition, there might be a combination like what is present currently on the tape head of tape 1, what is currently present on tape head of tape 2, tape 3, and so on up to tape n. So this will be a combination for that matter, right? For this, your diagram is supposed to say go to state Q1. Suppose it is set to go in state Q1 with making changes to the tape symbols, right? So tape 1 will have some change, tape 2 will have some change, tape 3 will have some change, and likewise tape n will have some change, right? Now this change will not be same. So I may have a change in tape 1, like I get replaced blank by A. In tape 2 I may have A replaced by, say, blank, or tape 3 I can have B replaced by C. In tape n I may have blank replaced by A, or I may not have any change for a tape. For example, tape 5 is having blank, I am keeping it as blank, or A I am keeping it as A, right? So what I mean to say, each of this change that is happening to the tape head is independent, right? So these changes are not common. So every tape will have some independent change. But as far as my state transition diagram is concerned, I may have a unique move from a state Q0 to, say, Q1 for a given combination with the tape symbol of all the n tapes, Now, as these tape heads will have their independent moves to be made, they will have their independent tape head moves also, right? So tape 1 can maybe go to right, or tape 2 can go to left, and tape 3 can remain stationary. Likewise, all the tape head moves after that transition will also be independent of each other, right? So whenever we represent this type of transition for a multi-tape Turing machine, usually when we write a transition for a normal Turing machine, how we write? Q Cartesian product with toe union blank gives Q union HA or HR, Cartesian product with toe union blank, Cartesian product with either left, right, or stationary, right? Because this represent as one state. This is a single tape which represents the tape symbol before transition. This is the state in which your diagram goes. This is the tape symbol after transition, and this is what may happen to your tape head in the form of left, right, and stationary. Now this is for a single tape, right? This is for a single tape for a normal Turing machine, right? But now in a multi-tape Turing machine, we don't have a single tape here, right? We don't have a single tape here. We don't have a single tape head here, right? So we have n such tape heads. We have n such tape actions to be performed, right? So how we write the transition function for multi-tape Turing machine? So the transition function for the multi-tape Turing machine is written as delta as Q Cartesian product with 2 union blank for n tapes. Usually we used to have only for a single tape, but now this will be for n tapes, gives Q Cartesian product with Q union with HA or HR, Cartesian product with the tape actions that we are going to take for all the again n tapes. Here we used to have only a single tape, and possible tape head moves in the form of right, left, and stationary again for n tapes. So if you see the difference, here we have n tapes, then here we have n tapes, and here we have n tapes, but the state transition remains same for the particular combination. So this is how we describe a multi-tape Turing machine, right? So we can use this kind of multi-tape Turing machine to work on different inputs at the same time. Suppose I give you a Turing machine, for example, to check whether the given string is palindrome or not, right? So you have one Turing machine, and the string which you wish to check is accepted by that palindrome or not. Where you will place that string? You will place that string on your tape, right? Then you will run your Turing machine, and at the end of that you will either comment that this is a palindrome or it is not, but it will be only for the single string that you have kept on the tape. Now suppose I have 10 such strings to check for whether they are palindrome or not, right? So if I have a single tape, I have to execute the Turing machine for 10 times because I have a single tape. So first string I will keep on tape, I will run the Turing machine, I will get the answer for the first string. Then again I will place the second string on my tape, I will again run the Turing machine, I will get answer for my second string. Likewise, I will keep 10th string on my Turing machine, I will execute the Turing machine, and then I will get the answer whether it is palindrome or not, right? But suppose if I have 10 tapes now, right? So on this 10 tapes, I will keep all 10 different inputs, correct? 10 different strings. Few of these may be palindromes, few of these may not be palindrome. And then I will run my Turing machine. So this Turing machine will now run on each of these tapes. Are you getting this, right? And then I can get output for all the strings in one go. So likewise, wherever I want to perform multitasking, there we can use this particular approach of having multiple tapes. Now we should also understand that if you have a Turing machine with multi-tape, you can convert that Turing machine into a single tape Turing machine also, right? So every multi-tape Turing machine has its equivalent single tape Turing machine, right? So there is a theorem for this. If you go in detail, you can refer the textbook and you can go to that theorem, right? So we don't have theorem in our curriculum, but still out of interest, if you want to look, you can see that every multi-tape Turing machine have a equivalent single tape Turing machine, right? So what, as far as your exams are concerned, you may have a short note on multi-tape Turing machine. So you can explain what is the phenomenon of multi-tape Turing machine, what is the significance, how it is different from a single tape Turing machine, what is the transition function for a multi-tape Turing machine, and you can also explain the configuration, right? So usually when we write ID notation for a single tape Turing machine, how we write? So state followed by the XAY, where X and Y will be your strings over to union blank, right? And A is a single symbol from your to union blank. tape head is pointing to A. This is for a single Turing machine, which you have already seen, normal. Now for multi-tape Turing machine, how you will write? So you'll have state will be 1 only because state combinations are unique. But now for first tape, I'll have something. For second tape, I'll have something. For third tape, I'll have something. Likewise, for nth tape, I'll have some configuration on my tape, where A1, A2, A3 up to AN are single symbol from tape symbol or blank, whereas X1, Y1, X2, Y2, X3, Y3 up to Xn, Yn are strings over to union blank, right? So this is how you can write a short note on the multi-tape Turing machine. So we have seen two variants up till now. In the last video we discussed about universal Turing machine, and the second variant that we have discussed today is multi-tape Turing machine.